I'll just quickly review the California data set for those of you who missed it, because I know some of you missed the lecture last time. So obviously, we all live in California. Some of us own homes. Some of us aspire to own homes. So, we either own homes or aspire to own homes one day. The thing in our mind says, is it a good time to buy? And if you do own a house, are our houses appreciating, right? Or is it going down? Because, like most Americans, our assets are a large part of our wealth is in the homes. So this is a good problem to look into. It's slightly old data from the 1990s for the California housing prices. This particular thing, I believe, I did it in Python. Right? And a very good exercise for you would be to do it in R. Right? See if you can do it in R. It'll be very easy. Just follow the way I have done the previous data in R. And for example, the Irish data set, I believe I did it in R. So just follow that illustration and you'll be fine. So we have this data in which the only categorical variable is the ocean proximity. So this is basic summarization of the data, exploring what it is, projecting it onto a map. This is using the Fourier maps, and then this is putting it onto a scatter plot. In this scatter plot, the color ranges are the home value, the median home value in a given.
Asif, Srinivas here, just would like to say there's a call in user 2. Not sure who there's a lot of background noise. If people could mute themselves, we could listen properly.
Yes, please do that.
Who's calling user 2? Please mute. Or ask if you could mute or ask somebody to mute.
Call user 2 indeed.
Yeah.
Could call user 2 identify themselves? We have no idea who it is. All right, I've muted call user 2.
Thank you.
So now looking at this, we have a scatter plot where these are the home values. One interesting thing to know that 25 years ago, $500,000 homes were the expensive side of homes. Do you notice that? They're deep colored, the 500K homes. Now in 25 years, I suppose a 500K homes, would it still be considered expensive? What do you think, guys? Anybody?
I think now it would be considered cheap.
It would be considered quite cheap, yes. So this is how times change. This is it. And here the size of the bubbles are the population density. So one thing is pretty obvious. We know it from experience. High population density areas tend to be expensive for housing. Right? Those are the urban areas or metro areas, and homes there tend to be expensive. Just looking at this map, you can tell that this is the San Francisco Bay Area, and that this is the Los Angeles area. And down there, you can see the movement from Los Angeles all the way towards San Diego. And then if you go up here, you can sort of make out the progression towards the Sacramento area. You can see the homes along the Central Valley, right? All the Merced and Fresno and so on and so forth. So there is a lot you can decipher just from the scatter plot. So that's that. Now, so there are certain observations that there is so when you look at the histograms, you'll see, and again, I talked about the skew in the data. Think about why there's a skew in the data, right? It is something worth thinking about. Whenever you see a right skew like this, or a right skew here in median income, is it true what it is trying to say is that the median income tapers off, and then most people have a median income comparable in a comparable short range. Then likewise population density. By population here, but is population per block. Right? Total number of rooms, most people don't tend to have that many rooms in a block. The violin graph is, of course, the density estimators. We talked about it, the box plot. So guys, if you don't understand these things, I've explained it once. So post it to Slack and then I will explain it. And remember, we also have the extra sessions. So we covered some of this in the extra sessions that I gave. I won't go over that again, but this is just a review. The correlation plots and so on and so forth. Once again, if you guys need me to explain anything, let me know. This is a pair plots. One more thing I added was the missing value. Whenever you get data, data never comes perfect. You always have some rows which are missing some features. For all sorts of reasons, somebody forgot to take measurements. Taking measurements was not feasible, right? Or the values were invalid and somebody had to delete it, and things like that. So you should see whether how clean the data is. And looking at this data, it seems that all the fields, all the features are there. The only place you have some missing values, about 7-8 missing values, is in the total bedrooms. And so these are total bedrooms, 7-8 missing values out of more than 20,000. A sensible approach is to just go delete those rows. It wouldn't affect your analysis too much. So this is the way you would remove those rows from the data. So this is that, guys. Now, there is one thing I just wanted to warn you. These days, network science is becoming a fast emerging subject. We have all sorts of networks in the world, the social network, the professional network, the network of power grids and power transmissions, right? The highway network, and many, many such networks. Even at the molecular level, in the biological systems, we have the protein networks, right? And the genetic code networks, and so on and so forth. And a lot of them have tremendous impact on, their structure, their topology, have a lot to say. For example, you can tell if there are vulnerabilities in the network. Some of you remember that at one time, the whole eastern seaboard went dark because some critical power stations failed. And because they failed owing to overload, they led to cascading failures, and the whole eastern seaboard went dark. And so we can today study those things, those vulnerabilities in network infrastructures, through a subject, through an exploratory analysis, through a machine learning exercise, and all of that comes under the subject of network science. So when we talk about networks, we start with simple networks. The first thing is networks is something you are not probably used to studying in depth. So I put a mention here that these notes are very preliminary. I'm still writing them. But see, you can have, let me give you some intuition. This is called a connected network. Means every node, you notice, is connected to every other node, right? So from any node, you can go to any other node in a single hop. Are we together, guys? So when you have that, the number of edges is much more than the number of nodes. In fact, it is n choose 2, which is n minus 1 over 2, which is, so in other words, the number of edges grows quadratically. You can see that for 10 nodes, you have so many edges. By the time you go to 50 nodes, it begins to look like a beautiful and abstract art. The same graph, isn't it? You can hardly see the links from one to the other, right? But the reason I put it here is to show how quickly the number of edges explode. Yeah? It's a quadratic growth curve. And these days, of course, we are all very well aware about exponential growths in view of the current corona and so forth. So that is it, that's one. There's another kind of network topology, which is a hub and spokes model. At the center is one hub node, and all other nodes are directly connected to the hub, but they are not connected to anything else. So one of the things we speak of in networks, or when we explore networks, is the diameter of the entire network. It is that what is the maximum distance between any two nodes. So what would be the maximum distance between any two nodes, guys? Could somebody tell me what's the maximum distance between any two nodes?
Diameter.
That's right. So how many edges are there? Let's say that if I take this guy and any two nodes in this, except the hub, remove the hub. From here, how would I go? You realize that all you have to do is from any node, you have to go to the center, the hub, and from the center, you can go to any other node, right? So it takes two edges at most to reach from any node to any other node. You see that, guys, in a star topology, the diameter would be 2, right? 2 edges. It takes 2 edges to go somewhere else. Then a variation of the star is a little bit more connected. It is the wheel. You see the wheel? It is like the star, except that a node is connected to its adjacent nodes. Every node is connected to 2 nodes, 2 neighboring nodes. Do we see this, guys? The wheel graph. Yeah. This is the wheel graph. And then there are other kinds of nodes or networks. This is very interesting, and it tends to show up often in practice. It is called the cliques graph. The cliques graphs are interesting. Each of these, do you see this bunch of nodes together? So each of these nodes are highly interconnected. Means every inside a clique, it is always or almost always. I mean, sometimes it's approximate clique, but strictly clique is in a bunch or in this group. It's called a clique. Every node is connected to every other node, so it's a completely connected subgraph. And each of these cliques are connected by just one edge. Do you see that there is only one edge connecting a clique to its neighboring cliques?
Asif?
Asif, one question. Sorry. The document is in which language?
Okay.
Oh, at this moment, yes, it's very nice. I trust you guys all know Latin. No, I'm joking. Actually, I still have to write the text. As I said, this chapter is unfinished. This is just placeholder text. There's a few
Okay.
web development group now. So up to here, up to cliques, it was fine. After that, there is a whole bunch of things that are handwritten, and I need to type that in. So that is why you see this strange language. And remember, this chapter is unfinished, guys. I'm still writing it. Okay? So now, one of the things that you speak of in network is something called the degree of a node. What we find in networks is that real life networks are very different from these simple conceptual networks, the wheel, the cliques, and the star, and so forth. It's not that these things don't show up in nature. They do in the complete graph. They do show up. For example, the complete graph, this one, used to be one of the very popular networks for parallel computing. But the earliest topology for parallel computing was this. Every processor had a direct link to every other processor. Some of you from hardware and parallel computing background will probably remember that, right? And of course, we went to different architectures, like Torus architecture, etc. And if you really think about it, all of those parallel processing architectures are networks, different topologies of the network. Right? And we'll have a lot more to talk about it. Actually, here, I discuss the parallel processing architecture that you find in practice quite a bit. I speak of the Torus architecture, and I will speak of the so-called binomial tree architecture and so forth. But I have not finished writing that. So now to analyze it, real networks, like what you see, for example, in the social graph, or a professional network, or a citation network. Citation network is when a researcher writes a paper, he cites, or she cites other papers, other resources. And you don't have to be a researcher, just an author. For example, if you look at the bottom of this document itself, you will notice that I have citations to all things that I found worthwhile. So now those people refer to somebody else and so on and so forth. So there is a web of citations. They form a network. Users, web pages form a network. So all of these networks in real life, they tend to show some very interesting behavior, qualities that are worth remarking. So I'll start with the simplest quality. The first quality that you observe in a network is the nodes have different degrees. What is the degree of a node? how many other nodes it is connected to. So given a node, suppose it is connected to 7 other nodes, its degree would be considered 7. Now, in directed graphs in which the direction matter, you can talk of 2 kinds of degrees, the in degree and the out degree. How many nodes are coming in and how many edges are coming in and how many edges are pointing out. Right? So, for example, a citation network could be treated as a directed network. But let's keep it to a simple thing, undirected at this moment. So the degree is the number of edges incident upon a node. Right? How many nodes is it connected to? So that's the degree of the node. It is quite instructive, actually, to see in a graph how the degree of a node is distributed. One of the earliest breakthroughs in this field was actually studying the degrees of the nodes in various network topologies. And if you can understand the degree distribution of a network, it is somewhat like doing descriptive statistics on a bunch of numbers. It gives you a very good sense of what is it that you're looking at. Now, degree is the simplest of it. Now, there are other measures, for example, connectedness measure, then clustering measure, and so on and so forth. And we'll talk more about it, but I'll just take the degree here. So this is a little utility I have, which I use to compute the degrees, because at this moment, there are no good libraries that automatically give it to you. Now, the library that I use is a very popular library called NetworkX in Python. And for R, it is iGraph. Both of these are very mature libraries. iGraph is much faster because the underlying implementation is in C. NetworkX is implemented in Python. So its advantage is that it's very Python friendly. Its disadvantage is perhaps of all the industrial strength network libraries, it is perhaps the slowest. But the fact that it is very intuitive makes for a great beginning. The general practice is that if you are in the Python world, you start with NetworkX. If your network becomes too big or it becomes too slow, then you move on to another library. And iGraph exists in Python, NetworkKit. There are many libraries these days that you move on to. But for learning, certainly NetworkX, and for experimentation with smaller graphs, this is certainly one of the best. So here's a little utility I wrote that you are most welcome to read through. What it does is, and so I look at one particular graph. It is the so-called Karate Club network. It's a classic, it's one of those things, it's like the iris for normal tabular data. Think of it as the iris dataset of the network world. There was a Karate Club in which, if you look at this Karate Club, let me explain how to interpret this graph. Do you see the color bar on the right-hand side, guys? This color bar gives you the color of a node. The color of a node is the degree. So things, for example, that have, let's look at this node here, where my mouse is. This node is yellow in color. The color matches here, right? Approximately this. It is because its degree is 2. Why is the degree 2? Because there are 2 edges coming out of it, right? Now, let's look at this node. This seems to be dark, sort of a maroon kind of a color. Now, how many edges are coming out of it? How many nodes is it connected to? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So there are 15 edges to it. So the degree is 15. So you can see the color of this is approximately the color here. Do you see the relationship, guys? So the color and the size is also a measure of the degree. I've made the nodes with bigger degrees, bigger, quite literally bigger in size. So looking at this, you can quickly establish that there are 2 key people in the Karate Club who are highly influential, so that almost everybody is related to one or the other, right? So in this karate, if you look at this, what can you infer as a data exploration exercise What is it that you can infer? So, well, at this moment, it's a little hard because you're new to this. I'll give you the idea of what it was. See, what happened with this karate club is, after some time, it split into two. It became two different camps of people, right? That karate club became two sub-clubs. And in a way, you can see who the sub-clubs will form around. One sub-club was formed around these people, and one sub-club was formed around this person, this hub. So in real networks, you always find these hubs or nodes of high influence, of high degree. And you should always search for that, like how strongly is the influence spread out in a network. So one example, which I believe gave in the extra class was this, that in one company, there was a problem. The problem was that the upper management, the executive levels, whatever they wanted to convey to the company, and they made a lot of effort to communicate to the employees of the company, and those employees would somehow come to entirely different conclusions, or their information would almost always be distorted or not correct. The company was very frustrated on what was going on. Why is it that they were trying to communicate, but what was being believed as truth on the ground and the grassroots level was entirely different? And why transparency was not having any effect. So if you, then one of the researchers made, actually Barabasi, one of the great researchers in this field, made a graph, a network of all the people who are communicating with each other. And that's a point of interest because it shows who the influencers are, who the central people are, or the hubs are, to whom a lot of people reach out for information. So one would imagine that in a hierarchical organization, as companies are, the people you would reach out to would be up the food chain, up the management chain. It would be the vice presidents or things like that. But actually, that's rarely true. In this particular case, they found a person who was of very high influence. Can you guess what that person turned out to be? Anyone would like to guess that?
The safety training I read the books.
Something like that. Very close, actually. It turned out to be an IT guy who was going about fixing printers and computers. So because he met people from every department and he talked with them, he became the vehicle to spread gossip from one team to another or misinformation from one team to another. So they realized that actually it was through his movement that a lot of information or misinformation was flying through. So it raises an interesting question. What do you do with this person? Do you fire him or do you do something else? Anyone would like to suggest?
Leverage him to spread good information.
Exactly. So what you can do now is, you know, somebody who is a good conduit for passing information, correct information along. So you make sure that he is educated on the right information, so that as he goes from team to team, he conveys or propagates a truth rather than gossip. Right? So that's the value of network analysis. It's quite an emerging field. In fact, if you look at the number of research papers coming out on this area of machine learning, it has an exponential growth. Let's say that it's spreading like a virus, like a coronavirus almost. It's an exponential growth. Huge amount of research is being done in this field at this moment. Very, very hot. So I thought that, and this is the first time I'm doing this, that the time has come to integrate it into a standard course of machine learning itself. Now, the work in this space, the earliest work was done by by two people, Erdos and Renge. Erdos was, of course, such a great mathematician that everybody has an Erdos number. Like, how many links away are you from Erdos? So this work was done, I believe, in 1957. He and Renge, another great mathematician, they posited that if you take n nodes and you take a probability P that any two random nodes are interconnected, then you can have what mathematicians call a binomial distribution, a bit of what the degree will be. So there's a certain probability that a node will have degree 1, certain probability that it will have degree 2, and so forth. So if you look at the degree distribution, it looks like this. This will be reminiscent to some of you of a bell curve or a binomial distribution. Right? I hope it does look like a binomial. Now, in the case of very large numbers of nodes and very, very low probability that two graphs are connected, it's a fact, a mathematical fact, that binomial distribution becomes a Poisson distribution. Now, I won't use all these mathematical terms because many of you may have forgotten what binomial is and what a Poisson is. It's there in the notes. Gradually, you'll become familiar with it. And as you go into intermediate machine learning, of course, you'll become much more familiar because I'll systematically be teaching it to you. Those of you who took the mathematics of data science, Vishal, you must be remembering this, one of the distributions we covered. So, yeah, so this is it. So it's a very interesting thing. Do these distributions happen in nature or in real life? Does the Erdos-Renyi, or these are called random graphs, I should have said random networks. But do these happen? Yes, there are situations where these sort of graphs show up. But it turns out that the vast majority of real life graphs do not look like this. They look like something which in an idealized form is like this. Okay. By the way, this is in the Erdos-Renyi. I have colored the degrees of the node. You can see that the degrees of the node are, pretty well distributed. There are very few nodes of very small degrees, very few nodes of very high degrees, and most of them are intermediate degrees. So what is the alternative to that in real life? One of the alternatives that was proposed by researchers, Barabasi and his student Albert, in 1999 was the so-called Barabasi-Albert network. It was considered a landmark in this field, and right after that, there was an explosive growth in this field. A lot of people were studying it, but now we know in hindsight that the work that Barabasi-Albert did, I'm told, was actually done by a great mathematician named Price. It wasn't quite understood at that time, or importance was not well understood. A great Price actually discovered this sort of networks. And that was in the 1960s that he discovered. 1965, I believe, is when he wrote his first paper. And that paper was way ahead of its time. It already contained some of the central ideas. And people essentially rediscovered it 30 years later. But for what it is worth, what does this graph look like? Can you see that this graph looks different from the previous graph, guys? Now, if you stare hard, you may start noticing that some of these nodes, they have very high degree. You see that? They're highly interconnected to other nodes. Whereas but there are also nodes which have very poor which have degree just 1, 2, 3, right? Low connectivity. So if we plot this graph, and this is a mathematical relationship, it is called a power law behavior or the scale free behavior. It is not, today in experience, we know that it is not strictly followed, but it is approximately followed. That the degree of the probability that a node will have degree D, in other words, the probability that a node will have D connections to other nodes is actually proportional to D to the power minus gamma, where gamma can be 2, 2.4, or something like that. Let's say gamma is 2. So then what it would mean is probability is 1 over D square, right? D to the minus 2 is D square, 1 over D square, right? So it falls quadratically with D. And this sort of graph, and we can see that when I draw it out with the degree of a graph visible, do you notice this, that most nodes have very low degrees, they are light yellow colored. Only some nodes are orange and very few nodes, in fact, only one node and maybe another node look like maroon and maybe reddish, right? Degree 40 or 50. So there is a very skewed degree distribution in this. And it becomes more evident if I replot this graph, and you should always do that when you're observing a network data. Try to plot it like this. You notice that this dark node, and very quickly it shrinks in sizes, and most of the nodes are yellow. They have low degree. And if we make a histogram, a frequency plot, look at the frequency plot here, which is so different from the frequency plot of the Ardos-Renier graph. It is some nodes. Most of the nodes have degree close to 1, 2, 3, 4, right? Whereas the nodes with 45 degree, let us say 42 degree, is right here, where my mouse is at this point. One node seems to be out here, one or two nodes, and just one node seems to have a degree about 22, 24, or something like that. Most of them have smaller degrees. So you see a power law decay, something like 1 over x squared decay, 1 over b squared decay. So this was the crucial observation that was initially made by Price in 1965 and later rediscovered by a whole bunch of researchers, and amongst them Baravasi and Albert. Right? And it sort of created a renaissance in network science as a subject. The number of papers that began to come out in this field went through exponential growth after that. Right? And it is still rapidly growing. People are finding all sorts of very, very interesting things about these networks. Right? And when you couple this real life networks, social networks, with one particular class of machine learning algorithms called deep learning or deep neural nets, there's something most marvelous. Some very good insights begin to emerge, and that is one of the very hot areas of research, and where people are creating a lot of companies and doing a lot of startups, and a lot of things are happening. It's a cutting edge at this moment. So now I'm going to look at another example, a real life example. So till now we were looking at the theoretical graphs. What do you find in nature? There is a Baravasi-Albert model. There is an Ardos-Renier model. There's complete graphs, star graph, wheel graph, and so on and so forth. So now let's look at a real example. At this moment, I put one example. This is a Facebook social graph. We all use Facebook. So this is a small group, I think centered around some topics of Facebook, a friends network. And we are going to look at this. So ignore this Latin thing here. Now see how rich actual graph looks like. I hope if you just stare at this, guys, you realize that it does not look like any of the basic wheel graph or complete graph or something like that. It looks very rich. I hope you can appreciate that, right? And you can see literally communities here, right? And in networks, you have communities of people who are very closely knit with each other. Are we together? And you find these nodes which are very high degree. You see this node here where my mouse is, it seems to be connected to so many nodes out here. There seems to be a big community of nodes out here. Yeah, you can literally mark circles around these communities. And in a later version of the graph, you'll see that I would have colored the communities differently. So I don't know, guys, when you look at this graph, it is absolutely breathtaking. It tells you a lot about human relationships, human friendships, and how people relate. I hope some of the beauty of this sort of graphs, real life graphs, it does show through in this. And this is part of the exploration of graphs and its properties, which is quite interesting these days. The amount of code needed to do this is actually pretty small. We read the graph and then we just visualize it. Couple of things. Why did there's an alpha transparency. Make the lines semi-transparent, otherwise it will become a big blur of ink, right? Excessive ink. So to not have a big blur of excessive ink, there is a typo here. This thing should be here. It should start with that. Okay, I'll fix that. Copy paste, this code has gotten a little bit manual. The indentation is wrong. Line 11 should start here. I'll fix that. So if you look at this graph, the social graph, and you ask what is its degree distribution, its degree distribution is this. So of all the topologies that you saw, the Erdos, Rengi, all of those, the wheel, the complete, and the Barabasi, Albert, which of these do you think it is closest to? Anyone would like to venture a statement? Which of these is it closest to, guys? Let's speak up.
Closest to real network, you mean?
Yeah, which of this real network, which of the theoretical networks that we talked about in the previous sections is it closest to? So see, remember this Barabasi, right? Exactly.
Yeah.
It is closest to the Barabasi network. And this is a very crucial observation that, and Barabasi's network, it may not be exactly that, but it is somewhat similar to that. And here I have visualized it with the degrees highlighted. You can see that they are, you see this node here, this at the very center is dark maroon. So it has a very high degree. Actually, I wish the y-axis and I could make it clearer. I'll do that. But you can see how well the distribution of this shows through. So this is an example of network science, guys. There's a lot to it, and I will mention because I haven't talked about clustering, I haven't dealt with communities, but you can see the communities. That's the next topic I'll add to this. I would highly invite you to go pick your own networks. And there are repositories of networks. There is an entire website called networkrepository.com or .org, where people have archived all sorts of networking data. It's become that hot, right? There is also a repository maintained by Stanford called Snap repository for network graphs. In fact, this particular data came from the Stanford repository. It is a sample of Facebook data. And of course, if you look at the kinds of network we live in, for example, Facebook, it is a gigantic network of what, about 4 or 5 billion nodes. Unless you have a really powerful computer, it's a bit hard to visualize. So, but anyway, something for you to play with. Now, the second thing I wanted to mention about this is that last time we did univariate linear regression. So the lab of it, actually these are the old notes. I'm still converting it into the new format, but the content is all there. So this is the linear regression. At this moment, please follow through and repeat it in your this thing, and in due course of time, I'll reformat it. So this is the lab we did last time. Please follow through. We covered it last time. I won't cover it now. Today, we have a new topic, but I'm just summarizing what we did last week. So here are the labs. Please repeat it. If you get stuck, reach out. We'll help you. Right? And then the next lab, which again, today I won't cover. I'll let you try to do it on your own. And then we'll cover next time, because we are alternating between theory and labs. So today is a theory session, so I won't go into that. It's a pretty, here's the Python version of the same lab. Then I'm just obviously scrolling through it very, very fast. And you will see that then we do the nonlinear version of this lab, nonlinear least squares. Read through this, guys. Follow through, read through. We have a lot of material to cover, so I won't be able to do every single example in slow depth, but I will certainly come back to it next time. So this is for the univariate, but nonlinear least squares. Suppose you know a function and you're trying to fit the function to it. How would you do that? Well, this is a little bit of a page which says that people often ask R versus Python. Again, I should move it to the top of the document. Never ask that question, guys. It's not R versus Python. It is always R and Python. And in a few years, it will be R and Python and Julia. So start doing these labs, guys. If you haven't been doing the labs, you'll be surprised at how much work or how much homework is waiting for you to do. Right? So get started. You have to practice a lot to become good at it. And this is the third one. This one deals only with real-world data sets. It deals with the famous data set of cars, the mileage of cars. It deals with Boston crime data set. It deals with, pricing data set for car seats. These are all classics of this field, really worth learning. There's a tremendous amount of learning embedded in these data sets. I won't go into too much of it because we're going to cover it in depth in the next lecture, in the next session. But I'm just giving you a very quick preview of these, lightning fast preview of these things, just to give you a sense that you need to get busy doing things, practicing the labs. Then this section of the document will contain all things interesting. So I haven't put it here. One of the things is the bias and variance errors. Remember in the previous session, I talked a lot about the bias and variance trade-off. Bias is when your model is simpler than the ground truth. Variance errors come from your model being more complex than the ground truth. And so it turns out that the way I explained to you was a good way to get started with. Okay? And everything that I said in those handwritten lecture notes, I'm going to reproduce it here in due course of time. It is work waiting to be done. I will do that. But you'll find something more than what I got time to talk about in class. It is something that I will talk about in the deep neural network class. But here, I'm just mentioning the paper. You can actually realize the state of the art says that today, when you look at modern machine learning algorithms, the state of the art algorithms like support vector machines, random forest, gradient boosting, neural networks, the bias versus variance trade-off has become not a trade-off anymore. It has become a situation where you have to deal with bias errors separately and variance errors separately. There's a lovely YouTube video to watch. I highly encourage you to watch, and obviously ignore this Latin text because it's waiting for my explanations. And so, and this is the paper. If you like reading it in paper form, this is a lovely paper, a very thought-provoking paper, which gives you the state of the art on bias and variance. I'll be talking about bias and variance. Obviously, this chapter is work in progress. I'll come around to it. Then another beautiful thing is something called the exponential families. I haven't talked about it. I won't talk about it in the whole of the introductory workshop. I'll only talk about it in the next workshop. When I do talk about it, you'll realize that this is of tremendous beauty and importance. If you can understand something called the exponential families of functions, you feel that you have understood the root of a lot of machine learning ideas, because they all, one way or the other, center around as a sort of a universal family or universal formula, which on the face of it looks rather arcane, but when you unpack it, you realize that it pretty much explains in some sense or captures the gist of so many of the distributions or functions that you see underpinning much of machine learning. So certainly a thing of great beauty. And when you understand that, you will look at data with fresh eyes, completely fresh eyes. Right? And why is it that I'm bringing in such a arcane topic into machine learning class? Well, if you talk to any good machine learning researcher, they would tell you that they absolutely love the exponential families. They're very well familiar with it. They see it everywhere. You don't see this talked about in the usually coding or programming-oriented books on machine learning libraries. But I've always felt that if you understand the exponential families deeply, you have a much deeper understanding of one of the pillars of machine learning. So it is really worth doing. So you'll see it there. Then I've moved the tips, cheat sheets, documentation, all these things that you're familiar with. I've made it the last section, a section of its own. You guys are all familiar with this. So it is all here, the cheat sheet. So go to this cheat sheet and you'll find it there. Now, in case you're wondering, this labs is a lot of labs to do. It is indeed, guys. And I hope that you guys are spending time doing it, because we are at this moment in the monkey see, monkey do phase. Believe it or not, this is the way to practice. In the beginning, you just see and you repeat. But after a little while, very soon, it won't be repeating. I would not be giving you solutions to the problem. I'll just leave the problems with enough hints, enough milestones that you need to achieve or directions, and you'll have to do those homeworks on your own. And if you do all those examples that are there in this notes, trust me, you will be ready to deal with any kind of data set after that using these techniques, right? And then one of the things that I've started doing it is adding a glossary of terms. Like, for example, I use terms like supervised learning. So what is supervised learning? So I've given a little bit of an explanation of those terms. Obviously, this is very much a work in progress. So for example, I don't know if you're amused or irritated by my explanation of what mathematics is. Mathematics is what mathematicians do, I suppose. Right? Then obviously you have this bibliography of all the resources relevant to this field. Right? And this bibliography will expand. You know, when I learn a subject, it may surprise you to know that whenever I encounter a new subject and I want to go deep into it, I read books in a peculiar way. I go and read the preface of the book. I might read the introductory chapter if it gives a historic background. And then guess what I do? I look for the glossary, and at the end of the book or in the beginning, wherever it is, and I go and look for the bibliography, the references, because becoming familiar with the references gives you a very high level view of the subject, right? It is always good to read a book in conjunction with other books next to it, right? Because some things are well explained in one place, some in the other. I highly encourage you to get some of these books. At this moment, I've asked you guys to get only 3 textbooks. One is the theory textbook, the yellow jacketed book, the Springer book, ISLR. The second is the R book, and the third is the Pandas book. That should be sufficient. But think of them as your core textbook, right? But that should not dissuade you from reading a lot of other books and other websites. So this is it, guys. This is a summary of what I have to say about the notebook. Now I'll quickly come to our reviewing our previous lecture. I'll give no more than 5 minutes to that. Let me know, guys, when you see the screen, the writing screen. Are we guys seeing the writing screen?
Yes, we can.
So this is a refresher of what we did. Last time we did multilinear regression. What is it? What are the factors that affect it? What is multicollinearity? What are outliers? What are the Gauss-Markov assumptions and Gauss-Markov? What is Gauss-Markov theorem? We had a little quiz. By the way, in the quiz, there were a couple of sort of a poorly worded question. In fact, there was a missing and crucial not missing, so that actually the answers were hard to give because, so we have fixed that. If you go back and look at the question, you can see the fix, and I apologize for that. But I hope that quiz was of some use to you. Then classification is something we'll talk about, but multilinear regression, what is it? When you can write an equation or in terms of multiple features. When you do that, geometrically, it represents a hyperplane. A plane in 2 dimensions, like with 2 features, it becomes a plane in 3-dimensional space. Otherwise, it is a hyperplane. Right? A generalization of a plane to higher dimensions is called a hyperplane. The Gauss-Markov assumption, what is it? Random means that your sample should be a random and true reflection of reality. Linearity means your hypothesis is actually a linear relationship like this. Y is beta naught, beta 1x, and so forth. The next hypothesis is, the next assumption is the normality of errors. Your errors at the end of the model should show a normal or a bell curve distribution. Right? The next is homoskedasticity. Actually, I believe I may have written the spelling wrong. It is homoskedasticity and heteroskedasticity. So these words are misspelled here. Let me fix it. Homoskedasticity and heteroskedasticity. This sort of reminds me of the story Mary Poppins. She taught the children to say a very long word that gave them a lot of confidence. Anybody remembers what that kid story was and what the word was? Supercalifragilisticexpialidocious. I don't know if you have small children, you remember that. So it's somewhat like that. I always say that in machine learning, when you come, sometimes it's a little bit of a fun to actually know the meaning of such a cryptic words, right? Big words. Well, there we go. So homoscedasticity is when the variance of the error doesn't change with y, right? The target variable does not depend on the target variable. Heteroscedasticity is when the variance of the error does depend on y, right? You see this funneling effect. Whenever you see this funneling effect, you know that you're looking at heteroscedasticity. I always mispronounce it as heteroscedasticity. I apologize for that. Right? And then what is multicollinearity? Multicollinearity, would somebody like to volunteer? What is multicollinearity?
Multiple predictors being related to each other.
Yeah, highly correlated to each other. Or one predictor could be expressed as a linear combination of other predictors. It's highly correlated with one or more predictors. So it leads to problems. In other words, the problem that it leads to geometrically is it makes gradient descent. It makes the gradient descent go into a funk. And so you end up with very unstable solutions. Okay? I won't go into all the details of it, but that's about it. Then we talked about interaction terms. You get interaction terms by mixing and multiplying the features together. Right? Polynomial terms. We talked about outliers. What are outliers? In one dimension, it's much easier to define. There's the Tukey's definition, amongst others, which just says that beyond 2 standard deviation, it's soft outliers. Beyond 3 standard deviations, it is a hard outlier, which is easy to do in one dimension, but in higher dimensions, it's a little hard. Outliers are data points, roughly speaking, which stand out from the rest of the data. And there's a whole body of literature and research and techniques, algorithms, if you say, of that help you find outliers in higher dimensional data, right? In 2 dimensions, you can still look at it, or in 3 dimensions and visualize the outliers. In higher dimensions, it's not so easy. So there's a whole set of techniques that you can use to find the outliers and remove them. Right? Then you also have points of high leverage that can screw your model. What are points of high leverage? Would somebody like to enlighten us?
Where value of predictor is very high, I think unusually high.
No, not value. Anyone else?
It's an observation within the already existing set of observations, kind of hiding within them, which unusually affects the model outcome.
Yeah, very good. So basically, it's an insidious data point. It is hiding in there, looking like normal. It doesn't look like an outlier. Outliers stand aside. You can spot them. But the high leverage points you can't spot. They're insidious data points hiding in there. But if you remove that data point from your sample while training, you get one model. If you include them, you get a completely different model, right? So they hijack your model building process. It is important to find points of high leverage and exclude them from your model building exercise. So that is it. So this is a summary, guys, of what we did last time, regression. I will close the book on regression. The rest of the regression we'll learn through labs. Next time when we do the labs, we'll have a lot to learn, and it will give us a very good review of everything we learned. But today is a theory day. I will now take a 5 minutes break, and we will start with a completely new topic, classifications and classifiers. But before we take a break, any questions, guys? So far, we have just reviewed what we did last time, and in the extra session. All right. If not, let's take a very quick 5 minutes break and no more than that. Let's regroup in 5 minutes and we'll start.
Can I just ask a quick question?
Yes, please do go ahead.
So I have 3 textbooks. One was the ISLR book. The second one is the Modern Data Science with R
Yes.
by Bomber. And then I bought the third one, which is the Art of R Programming. Is that I think the third one you mentioned was Pandas.
Pandas, yeah. The Art of R Programming is a good book. We can use it, but the one that I would highly recommend is now that you have the Modern Data Science with R, you can for Python also. So get the Pandas book.
Okay, that's fine. I had already ordered that book. It'll be here on the 18th, so that's fine, no problem.
And then there is another book which was by the O'Reilly book on Scikit-learn and TensorFlow.
Okay, so you're recommending to get that one as well, or?
Yes, very much. So guys, it looks as though I'm recommending a lot of books. Here is a way to approach it. Always first read ISLR, because nowhere are things so clearly explained as in ISLR. It will get your foundations right. Treat these rest of the books as practitioners' book. What will happen is today these libraries are there. Scikit-learn is there, TensorFlow is there. Tomorrow these libraries won't be there. Some other libraries will supersede them. So the rest of the textbooks will become obsolete. But the one book that will not be so obsolete, in fact, will still be shining, would be the theoretical book, the ISLR, because math changes very slowly. You add to it, it never gets obsolete. Right? So start with the ISLR, make it your root book. It's only 400 pages, guys, out of which we'll do only 350 pages. The other 50 pages refer to things that actually are not commonly used. We won't do that. 350 pages, but these 350 pages, if you can get it into your mind absolutely clear, you will have rock solid foundations in this field. There are not that many people who know it or have studied it so thoroughly that they remember everything that is there in the book. If you can, you have a winner. Treat the other books as helpful guides while doing the lab. That is their purpose. You won't learn theory from them. You will learn the specifics of libraries, the R library, the R language, the Python library, Scikit library, sorry, and the TensorFlow library and the Pandas library. So those are library coding related books. Treat them as references and use them as such. They're excellent books, but they're also the sort of knowledge that gets dated very quickly. Right? So for example, we are talking about Scikit-learn and TensorFlow. Scikit-learn is still going very strong. TensorFlow, well, the world has surprisingly gotten quite divided. TensorFlow was released just a few years ago. It burst upon the scene, became the runaway success. And then already now there is a contention because there is a PyTorch. And most people are finding, researchers are finding that PyTorch is much easier, much more straightforward. And in fact, there is a huge migration away from TensorFlow to PyTorch these days. Right? So you don't know, libraries keep changing all the time. Maybe TensorFlow will be there 10 years from now as the leading library, maybe not. Maybe PyTorch will be the leading library, or maybe something completely different will be the leading library. Likewise with Scikit-learn and Python and R, and who knows, maybe Julia will take over all of these. But while all these libraries come and go, the one thing that will not change is the foundations of the subject, for which you should refer to the yellow jacketed tool. Right? Other things have a shelf life. They are of practical value. Any other questions, guys? So I'm going to pause the recording. Let's take, actually it's 8:16. Let's take a 15-minute break. Huh? Let's regroup at 8:30. All right, guys, we are on the record. Somebody had a question before I start? Otherwise, I'll get started. See, so far we solved this problem. Regression was simply put, you have a box, the X feature vector goes in, Xi, and what comes out is a Yi hat, which belongs to the set of real numbers, right? A number comes out. This is a regressor. You use the word regress regressor model or something like that, right? Now, a somewhat similar box is this. The X vector goes in, features go in, whatever features there are, and what comes out is again a label, a Y, which we call an output, but that output belongs to a category. An example of that would be, e.g., cows or ducks, cow or duck. You're trying to identify, is a data instance belonging to a cow or is it a duck, where this could be, let us say, weight of the animal, the size of the animal, the beak, whether a beak is present or not, and whether webbed feet is present or not, webbed feet, horns, etc., etc. Right? So this sort of exercise is a classifier, and this whole process is called classification. It is as simple as that. So now we will start studying the classification process or the classifiers. We'll start with the simplest classifier today. It is not just the simplest, but also one of the most powerful and most often used classifiers. It is called the logistic regression. Now the name is misleading because the name has the word regression in it, but it is actually a classifier. But before I go into that, let us clarify the meaning of the classifier word a little bit more. The quintessential example of regression that I gave you is an entrepreneur trying to sell ice cream on a beach and trying to decide how the relationship between the amount of ice cream he'll sell in his to temperature, wind speed, and so forth. In a similar vein, a quintessential example I can give to a classifier is that of a child who you have taken, or some children whom you have taken to a special kind of a meadow. Imagine a very simplified meadow in which there are only two kinds of animals roaming around. Either there is a duck or there is a cow. And then suppose you are looking at an animal and you're telling your child that, see, look at that animal. It's a small animal. It has feathers. It has webbed feet. It has a beak. That's a duck. Then a little while later, you encounter a cow. And then you point out to that cow and say, look here, my child, you see those big horns and you see that big animal with 4 feet, right? And a swishy tail and so forth. And what you're looking at is a cow. So now, in the beginning, let's say the children are all lost, right? Or they can't make head and tail of what we just said because you did what would be called adult talk, a lot of information. And suppose these children are 2-year-old, they are not getting it, right? Or 1-year-old or 2-year-old, they're not quite getting what you are saying. So now you point out to a random animal and you ask, is it a cow or a duck? Let's say that you point to a cow, new cow you encounter. You ask, is this a cow or a duck? Now, those children, if they have absolutely no idea whether it's a cow or duck, what will they do? They will just guess. So half of them will guess it's a cow, half of them will guess it's a duck, isn't it? Or the same child, you keep on showing it animal after animal, it will just randomly say cow or duck, and it will have a pretty high error rate. Then gradually the child begins to form a notion, and all these children begin to get the concept of a cow and the concept of a duck. They have some internal hypothesis in their mind. So one of them is that the small is duck, big is cow, right? Horns is cow, webbed feet is duck, beak is duck, and so forth. So now there is a formation of here, or there's a conception of an animal, right? You're beginning to distinguish between a cow and a duck because you have a concept of a cow and you have a concept of a duck, right? So once you form this concept, you're essentially forming a model or a hypothesis in your mind. And then you ask this child, is this a cow or a duck? The child will likely make less mistakes, may not get it perfect, But as the concept of cow and duck gets more and more refined, more and more accurate, or more and more precise, the error rate will go down. The prediction or the identification error rates will go down. Right? So that is the nature of classification, or this whole process is classification. What the child is doing is classifying the animals as cow and duck. And inbuilt to the notion of classification is the same concept of generalization that you saw with regression. In regression, we notice that you might have a temperature on a day which is not exactly there in your training data set. And yet your model is able to predict the sale of ice cream on that at that temperature, which the model has not seen so far. It is, in other words, able to generalize from the specific training instances to the concept of or a hypothesis about the relationship. In the same way, in a classifier, you say that a classifier has learned when it can generalize beyond the training data and it can make prediction for an animal whose weight and size and things may be different or may not exactly match any of the data instances you have encountered before. But if you can make predictions for that animals correctly, if you can identify that animal correctly, you say that you have a good classifier now because you have a model that can correctly classify. So far, so good, guys. Huh? So in classification, when you predict, it is not so much a prediction. It is more an identification, your best case guess of what it is. You're not measuring, you're identifying, is it a cow or a duck? Or maybe the meadow has three animals, cow, duck, horse. You're trying to now identify one of the three animals. The distinguishing feature is that in classification, the target variable is categorical. Means the output belongs to a finite set of possible outcomes. The outcome can be, or the prediction can be, or the identification can be an animal, but you cannot say some animal which is not there in the training data. So for example, there are no penguins in the training data. There is no way you can expect a classifier to all of a sudden call an animal a penguin. And your data, your subsequent data shouldn't contain a penguin. So you have to define a finite set of outcomes or objects, and the classifier will identify one of those objects. Those objects are typically called classes, right? Because it captures that notion. There are many, many ducks in the world, but they all belong to the class of ducks, class of animals called ducks. Likewise, there are many, many cows in the world. They all belong to the class of animals called cows. So these are called classes, and we use the word category. Category is a finite set of classes. Example, a category is category of animals on a meadow. Give me a moment. I seem to have on a meadow cow, duck. Or if you want to extend it, let's make it three animals just so that we don't stop at two. Cow, duck, horse. When we do that, this is your category. This is your category, the set of three possible classes. And you say that these are the classes. So this is the sort of the vocabulary that we use. Cow is a class, duck is a class, horse is a class. Right? And the set of all of these is the category. And so the classifier will take every feature vector, in other words, a data containing the weight of an animal, the size of an animal, whether or not it has beaks and webbed feet and swishy tail and horns, and then it will be able to identify which of the animals it is. Are we together, guys? Now, do we understand the concept of a classifier? So let me ask a quiz question just to make sure that we understood. Suppose you want to make a prediction machine that can tell based on some factors, let's say how much traffic you're seeing outside a shop on a given day, right? And how much the items are on for sale, what percentage discount you have on the items and so forth. Suppose you are trying to predict the amount of revenue that the shop will earn in a given day. Is that an exercise of regression or classification?
Regression.
Regression.
And why is it regression?
You're
We
using
have continuous data, quantitative
input
data.
to predict an output.
Yeah, we are predicting a number, a measure.
Predicting a number, yeah.
It's a measurable thing, the revenue. On the other hand, suppose I ask you to do this. I give you wine. Now, it turns out that wine can come from two kinds of barrels, some good barrels that were well preserved, and some barrels which for some reason developed problems, and the wine has gone bad. You are allowed to take drops of wine and measure some chemical attributes. Based on the chemical attributes, you need to tell whether the wine is good or bad. Is still good or has it gone bad? So a prediction machine, an algorithm that can take the feature vector containing the chemical attributes of the wine sample and tell whether it's good or bad wine, would you call it a classifier or a regressor?
Classifier.
And why do you call it a classifier?
Because you'll get two different outputs based on multiple inputs.
Yes, maybe more than two, but it's not something we are not predicting a number. We are just predicting yes, no, yes, no.
Yes, we are identifying the type of wine. Right? When you identify things, it is classification. It is not a measurable thing, good or bad. At least the way the question was posed, a wine can either be good or bad. Right? And that. Or let us make it even more drastic. Let us say that if it is good wine, you hold it up to the light and it will have qualities like it will look clear and so forth. And if it is bad wine, it will look terribly sort of foggy. But you are not looking it up to the light. You're just trying to determine, is it good wine or bad wine? That sort of thing. Another example is, suppose you are looking at, it's a common thing we do. You know the pregnancy test kits. You dip it in the urine, which looks at, I presume, some chemicals present in the urine, and it determines whether a person is pregnant or not. So is that device a classifier or a regressor?
I would say it's a regressor.
Regressor.
So that's the classifier, right?
No, but it's predicting one output, right? So
Yeah.
basically a binary number. Yeah.
So when it predicts a binary number, what is it? Is it a classifier or a? See, binary is this or that.
Like a spam or not, like yes. Like that's a binary.
Pregnant or not. It is one or the other outcome, right? You're identifying one of the outcomes. So is it a classifier or a regressor?
If you're predicting binary, I would say classifier, but
yes, it is a classifier because it says only two outcomes, right? It is not predicting. I did not pose the question as saying predict the degree of pregnancy. If there is such a thing. I mean, generally, when we talk of pregnancy, either a person is or is not pregnant. Right?
So I have a question on that because someone can correct me if I'm wrong, but I thought the idea was it's based on a threshold value, right? If it's measuring some hormonal balance, right? So if your hormonal balance is high by some value, therefore you're pregnant. If you're lower than that value, then you're not, which is where they fail. So like that's where I'm unclear. Is it binary or is it by threshold value?
It's actually a very good question. So I'll just repeat what Irfan said. He's saying that, see, internally that device must be measuring the levels or the concentrations of certain hormones, right? Now, I'm not a medical person. I don't know which hormones it would be, maybe progesterone or whatever it is. I really don't know. I'm just guessing. But whatever it is, you look at the concentration of that. And therefore, because you're measuring the concentration, it looks like regression. And you will encounter situations like this. But you have to ask yourself, what is the outcome? Whatever it does internally, what is it producing as an outcome? It's producing an answer, which is pregnant or not pregnant, right? In other words, in US, it is customary, I believe, for these pregnancy kits to have 1 bar or 2 bar or something like that. So the question is it 1 bar or 2 bar or something, right? So it can be either one or the other. So therefore, because the outcomes are finite and you're picking from the 2 outcomes, it is actually classification, though internally it may be measuring actually the concentration itself. So when you decide whether something is regression or classification, you actually don't look at the internal mechanics. You look at the outcome and you ask from an outcome perspective, is the outcome a real valued number or is it a class within a finite category?
So just to further that point, suppose you are looking for a value. So if you're saying, I don't know, maybe you're supposed to return a value of 50. At any point does this problem become a regression problem, or is it always going to be classification?
No, you pose it as a classification problem. Right? So any regression problem, if you attach a cutoff, becomes a classification problem, isn't it? So for example, you can take the problem of sale of ice cream on a beach. And I could pose the problem like this. Did you sell at least 30 gallons of ice cream or not? Right? So now what will happen? You predict how much ice cream you will sell. And then you ask yourself, my threshold is 30. Is it exceeding 30 or not? If it is exceeding 30, the answer is yes. If it is not exceeding 30, you say my answer is no. So you just converted a regression problem to a classification problem by applying a threshold. Is that becoming a little more clear now?
So Asif, this is Balaji. I think the main doubt is regarding the optimization techniques. I mean, one is where for each continuous value for which you want to hit the right number, that is regression. And here you want to be correct between the classes. And the optimization techniques, I don't know, you will introduce would be quite different probably. That is where the difference is lying, I guess.
Actually, the optimization techniques would be surprisingly similar. There are differences. The loss function is not sum squared error anymore. It will be something called cross entropy loss, but we'll come to that gradually. But think of it like that. What is your end goal? To measure or to predict one of the few types? Right? If you have to pick one from a category, then it is classification. If it is to measure, then it is regression. So let's take a few more examples before we continue. Suppose I were to ask you this question. Using all the parameters and all the turbulence that we are going through in the economic landscape, what will the Dow Jones Industrial Average look like in July? What will be its value? Right? Can you predict? Come again?
22,000.
22,000. Yeah. So what are you predicting? 22,000 is a number, isn't it?
Yes, sir.
So therefore, this process is regression or classification?
Regression.
Is regression. Exactly.
So, Asif, on the same token, right? If we were to flip the question as to in July, whether Dow Jones will be up or down, that becomes a classification problem then, right? The same calculation, but a different outcome.
Exactly, it becomes a classification problem. So this is where generally people who learn this subject get confused, that any regression problem can be made into a classification problem by simply putting a cutoff, right? Putting a threshold, and above the threshold we can call it one thing, below the threshold we can call it another thing. Right? Or
any continuous variable, sir, we can change it to categorical variable, and that's it.
By putting a threshold, yes. But the other way is not always true. So for example, if you are to predict whether your apples, based on all the attributes, will be a green apple or a red apple when it is ripe. Now, generally, green and red apples are entirely different. It will be either one or the other. There is no, I don't usually see apples which are halfway green and red. Isn't it? So it is not always true that it is a measurable and you put a cutoff. Apples are apples. You're identifying the species of apple, right? Or let us say that I give you a dog in a box. You're not allowed to see the dog. The dog barks. You can take the weight of the dog in the bag, in the box. You can hear the bark. You can see how much food the dog eats. And you have to tell which species of dog it is. And let us say that I'm giving you only 3 choices. It can either be a golden retriever, which is what I have. And let's say the other choices, it could be a poodle, or it could be a chihuahua. And now you have to choose between a chihuahua, a poodle, and a golden retriever, based on some features like the amount of food the dog is eating, the bark sound, the weight of the animal, and so forth. So now you realize that you're identifying one of the types. This is a problem of, what is it? Classification or regression?
Classification.
The telltale sign is that I said outcome has to come from a finite set, chihuahua, poodle, or golden retriever. And I was reminded of this example because I can hear my dog barking in the background. It's a golden. So things like that. I hope I'm making it clear what is classification and what is regression. Another example, and we will deal with this example in this workshop, is the breast cancer dataset. Suppose you're trying to determine whether a person has breast cancer or not. Now, the history of this is breast cancer is actually one of the scariest things for women. It is it's very common as cancers go. It is not at all a pleasant thing. So the test for it used to be invasive. You would go cut open surgically, take a piece of the tissue, put it under the microscope, and do all sorts of tests and come back and tell whether the person has it or not. So now, over the years, people have come up with a progressive set of tests. You don't do one test. The first thing you do is you just do a mammogram. If everything looks fine, you say, all right, you're fine. The second thing is if something looks suspicious, at least in many countries, if something looks suspicious, you would do what is called a fine needle aspiration. Go with a thin needle, aspirate out a little bit of a tissue, typically from the lymph nodes or something. And then you would put it under the microscope and you would observe whether the person has cancer. Right? Even if there's a small chance that the person has cancer, then you would go and do perhaps more invasive things. You would do a core tissue biopsy. In other words, now you would go and take a core of the tissue out, a pretty good section of the tissue out, and then observe that under the microscope and so forth. So there are layers. You try to start with the simplest and most non-invasive. If suspicion develops, you get progressively more invasive. So we will deal with one particular one called fine needle aspiration for breast cancer. This work was done actually a while ago. again in the 90s, and this data set is very instructive. So you get all sorts of measurements, features about the cells that you are seeing under the microscope, their diameter, their shape, concavity, and whatnot, many, many attributes. There are about 13 to 17 attributes you look at. Based on that, you have to come to one conclusion. The person does or does not seem to have breast cancer. So is this a question, is this a problem of classification or regression? Anyone? What is it, guys?
Classification.
Why? Because the possible outcomes are does have breast cancer, does not have breast cancer.
Yes and no.
Yes. No. That is it. Now let's take another example. In the last example now, we dealt with the California housing data. The target variable, suppose we take, is the median house price in a given block, city block. So you have to predict based on all sorts of attributes. I believe we had 9 attributes. Based on the 9 attributes such as longitude, latitude, proximity to the sea, right, population density, and so forth, and the income in that neighborhood, and so forth, median income in that neighborhood, total number of bedrooms, total number of rooms. All of these are what features about houses on a block, and you have to predict the median house value. Right? A median house value could be, let's say, $300,000, $700,000, $800,000. Mute yourself. So, was it Bali? Okay, all right. So, thank you for muting. So, this is an example of classification or regression. What is the target variable? It is, you have to predict the median house value. Is it a number, or is it a type? Is it a class? Who would like to?
The number.
It's a number. And therefore, a prediction engine that can do this would be called a what? A regressor or a classifier?
Regression.
Right. And so we will do this exercise actually as a regression exercise. So make sure, guys, that you have done the California dataset, the whole example you have followed through, because the next step is to do regression of that dataset. Okay? And I'm about to add the exploratory analysis of breast cancer data also, because we're going to do classification on the breast cancer data. So these things will become very real in your lab. So now that we have understood classification versus regression, let me take a very toy example.
So Asif, is there a use case where we use both of them together, regression as well as classification, instead of or it is and?
Oh, many such situations. For example, do you have diabetes? Or which category would you fall in? Not diabetic, pre-diabetic, and truly diabetic, right? Based on a whole set of markers. Now, that is a classification problem.
Yeah.
Once you have that, the next thing that becomes important is, can I predict the severity of your diabetes? And usually that is measured by something called a hemoglobin A1C. Based on your features, can you predict what your A1C is? And this has become particularly relevant in view of a recent and a remarkable discovery that was made, I believe, just last year. So let me talk a little bit about that discovery since you asked this question. There is such a thing as an optomap. Some of you who went to your ophthalmologist must have gotten a picture taken of your eyes, inside of your eyes. It's called an optomap. Do we all know those big round maps of the eye? So in the optomap, you see blood vessels, capillaries, and things like that. Now, usually the optomap was of value only to the ophthalmologist to check if your eyes are okay. But one of the most recent and startling breakthroughs that have happened in artificial intelligence and machine learning is that somebody decided to see whether it can predict more than just eye condition. And to their great surprise, it could fairly accurately tell your blood pressure. It could fairly accurately tell your A1C, hemoglobin A1C level, the degree of diabetes that you have. Right? So now you can take the Optomap and you can use it either as classification. You can break people up into categories of non-diabetic, pre-diabetic and diabetic. And you can also treat it as a regression problem and guess the A1C, hemoglobin A1C, or the degree or severity of the diabetes. That is quite remarkable. Right? Do you see how you can take data and use it for different purposes? Anil?
Yes.
So that is one example that you can do. So anyway, all of this will become much more real when I take this toy example now. So I'll take two toy examples. One, we'll come back to our cows and ducks. Our cows and ducks are very illustrative. Let's take this cows and ducks. So suppose I take only two attributes, volume of the animal or size of the animal and weight of the animal. So if you look at the weight of the cows and ducks, and maybe horses also in the mix, would you agree that the ducks, what are ducks? Ducks are typically white. So they would be somewhere around this. On this weight versus volume coordinate axis, they would be somewhere around this. And cows should be, well, there are no red cows around, are there? Well, some of them can be somewhat reddish. Okay. Would you agree that they are somewhat like this? Would you guys agree that the data would look something like this? And the ducks would look something like this. Can you guys tell in what color I made the duck data? Ducks and cows. Are you guys able to see my writing?
Yes, sir.
And the cows are in which color? The data points for cows?
Red.
Red. And the ducks are there. And while we are at it, let's throw in should we throw in the horses too? I don't know. Horses, we need to give them a color. Well, for lack of a better option, I will throw in blue. Now, the horses tend to be not so big, but they are certainly heavy. So let me just say that they are like that. These are not up to scale and not very realistic. But let us assume that this happens to be something, a somewhat rough approximation to truth. Are we together, guys? And now we need to determine whether an animal is a cow or a duck or a horse. Let me mark it as horse. So how would you do that? Yeah, it's quite interesting. So to answer this question, first, actually, let me do one thing. Let me simplify the problem and let's take away the horses. We go to the meadow and we shoo away all the horses from the meadow. So now you have a meadow which has only cows and ducks. And let's try to solve the simpler problem. So if you make the frequency plot of this along the weight axis, would you agree that the ducks, their histogram or their frequency plot would look like this? The weight of the cows, this will be the frequency plot for the cow histogram. This would be the duck histogram. And along this axis, it would be like this. And along this axis, it would be like this. Something like this, guys. Does it make sense? Actually, let me make it like that. Do you see what these curves are? Blue curves are? These are just frequency plots. I made it upside down. It shouldn't be upside down, but it's just because I didn't want to overwrite the data themselves. But in the margins, I've drawn the histograms, the frequency plots. I hope the frequency plots are visible to you guys. Does it need interpretation, guys? It's just plots.
So the frequency is the number of cows in a given point?
Yeah.
Weight?
So you can see at the center, right? There are a lot of cows which have mass around the center. And to make this thing obvious, let me put lots and lots of cows here. A lot of concentration of cows, right? Something like this. So this is the frequency of cows by the weight and frequency of cows by volume. So if you look at only one axis, let's just look at one axis. In this axis, you have the ducks. And then you have the far away, you have the cows. You have the cows. And let's say that this axis is, what would you like to have, weight or a volume? Doesn't matter. Let me just take size. So you realize that ducks are small in size, right? And cows are rather big in size. So how would you write a classifier that distinguishes between a cow and a duck? You can say, well, that is actually, it couldn't be easier. What I could do is simply do this, find the center of the ducks, this peak of the duck, find the peak of the cows, right? And these two lines are there at the peak. This is where their frequency plots achieve their maxima, the bell curves achieve the maxima. And what can I do? I can then take this thing there. What I can do is I can find this distance and take the perpendicular bisector of this. What is the middle point of this? This. And I can call this with a big, actually, let me give it a nice big color. What should I call this?
Your boundary.
Let me give it a nice big color. Well, what color can I give? More colors. I've already used up yellow. I have used up blue. Let me use orange. Right. So this thing, no, it didn't become orange, but that's okay. Suppose this line. Suppose I put this line and I say everything on this side will be a duck, on this side will be a cow. Anything. So this is your cutoff point along the size axis. Do you think this will work for us? Guys, what do you think? Will this classification work?
No.
Why not?
Sure.
You didn't take the standard deviation into consideration.
All right, we can do that. In other words, what you're saying is the spread of this will be sigma 1 and sigma duck and sigma cow. They will be different. All right, we will take that. But generally speaking, okay, first of all, just assume that the standard deviations are the same to the first approximation. Don't worry about the standard deviation. So now, suppose the standard deviations or the spreads are the same. In other words, this hill looks exactly like this hill, which it doesn't. But we'll sort of squint our eyes and not look too carefully and pretend as though they are more or less identical, but they're just positioned at different places on the axis, along the size axis. Then would it be reasonable to take the perpendicular bisector of their peaks? This point. And on this side, it will be duck. On this side, it will be cow. So guys, let's say that the ducks are approximately 20 pounds plus minus some, actually 10 pounds plus minus some. And the cows are like 500 pounds plus minus some. Right? So would it be reasonable to pick a cutoff something like 250 pounds and say, or 200 pounds and say, well, you know what, above 200 it must be a cow, below 200 it must be a duck, something like that. We may be occasionally wrong. There might be a cow that is probably less than 200 pounds or something like that, but it seems a fairly good approximation. Anybody is convinced of that, guys? Especially if we assume.
Absolutely, yes.
Yeah, it is right. Yeah. So there is actually a name for this algorithm. To do so, it is called, and we did it in one dimension. The name for this algorithm is linear
regression
discriminant analysis. So in linear discriminant analysis, we pretend as though these two bell curves or these two frequency plots, they are identical. The only thing different is where is it located along the axis. So mu of duck, the mu of cow. And so you say that the cutoff is mu cutoff is roughly speaking a mu of cow plus mu of duck divided by 2. In other words, is the midpoint between the two. And so if your data point has size less than cutoff, you would say it's a cow, it's a duck. If it is more, you say it's a cow. So that is in one dimension. Now look at this data, it is in 2 dimension. We could have played this game with respect to both the weight also in a similar way. So when we generalize it to 2 dimensions, all it means is you take the center here of the ducks and the center of the cows, right? And join it with the dotted line. Once you have joined it with the dotted line, then your bisector of it this is your separator. This line or this thing is your separator. Any point on this side of it is a cow, is a duck. And any point in the feature space on this side is a cow. And there is a nice, lovely word that people use for this. This is called a decision boundary in classification, a decision boundary. Right? And here in one dimension,
How?
this is
What's your clause, you stupid?
This is the decision boundary. So in one dimension, a decision boundary is a point. In 2 dimension, it is a line. So can we generalize, guys? In 3 dimension, what will the decision boundary look like?
Plane.
Plane.
It will look like a plane. So this particular algorithm is actually the simplest one you can think of. And it was interesting. It was discovered, if I'm right, by the great statistician Fisher, who wrote the paper called Discriminant Analysis, literally. And the idea is very simple. Do you see how simple the idea is? So this is one of the classifiers that is mentioned in your chapter 4, and we should review it.
Asif, I have one question here. So why do you say that both of the distribution should be identical of the duck and the cows? Is that a requirement?
See, to have a linear discriminant analysis, to use this concept of a straight line boundary, a hyperplane boundary, plane boundary, that is a requirement. Now, in practice, what happens is they won't be the same. For example, cows and ducks, their distributions are certainly not the same. Ducks are what, 10 in weight. They will be 10 pounds plus minus maybe 6 pounds, right? On the other hand, a cow will be 500 pounds plus minus 200 pounds. So the variance of the cow will be much bigger than the variance of a duck. But it turns out that, see, when you build a model, you make a lot of simplifying assumptions. One of the simplifying assumptions you make with linear discriminant analysis is that 2 assumptions you make. One is that the instances of one class are all clustered in one place of the feature space, like, one region of the feature space, and the points of the instances of the other class are again clustered in a different part of the feature space. That is the first assumption, right? Or might as well write those assumptions down. Let me do that so that it becomes, yeah, assumptions. And by the way, these assumptions need not be true. It is a hypothesis that you are making about the world, about the data, that may not be true. Each class instances are clustered around a different in the feature space. In the feature space. Number two, these clusters are approximately, at least, a bell hill. A bell hill, you know, like a bell curve generalization, or a normal, or more formally, normal or Gaussian, people use the word Gaussian, distribution. Right? In simple terms, it looks like a bell hill. Right? A third assumption, which is only true only for linear discriminant analysis, LDA or linear DA, is that the hills similar, i.e. share the same variance. Variance is the spread. Red. At least approximately. And the fourth is what I'm saying. If linear, if bell hills are not, if the bell hills really do not look alike, then there is a little bit more complicated model. We have the quadratic discriminant analysis. Are we together, guys? If the bell hills really don't look alike, then we have another process called quadratic discriminant analysis, which is a little bit more complicated. It is not as simple as taking the perpendicular bisector of the two hilltops, but you need a little bit more complication to find the decision boundary, right? So I'll leave it as that. Now the thing is this always true? No, it is not always true. And this brings us to an important point about machine learning. See, every algorithm, it assumes a worldview. It assumes that the data looks like this.
No free lunch.
Yes, no free lunch theorem, exactly. But if the underlying data, if the ground truth does not match with the assumption, and there's no reason it should. Sometimes it will, and sometimes it won't. If it does match your assumptions even approximately, you will get a reasonably good model, good predictive model. On the other hand, if the underlying reality does not match your assumptions at all, it's completely different, then your model will perform quite badly. And you can never tell, right? You can never tell whether an algorithm will or will not work for this data set, because unless you already know something about the data since a priori. But in the absence of any prior knowledge, any one algorithm could be the right algorithm, because each algorithm has a different worldview of how the data set is represented in the feature space. Are we together, guys? So I will just stop at linear discriminant analysis for now. Notice how it sort of draws a perpendicular bisector, a line or a hyperplane, plane or hyperplane, by connecting the hilltops of the two classes. Are we together? Now the question is, what will happen if I bring in the horses also into the meadow? Now life gets very little bit more complicated. So let's try that example. What if there are horses too? That's the question we will ask. Right? So now category C is cow, duck, horse, isn't it? So now let's redraw the feature space and see whether we can generalize our results. Once again, our ducks are here. Let us say that our cows are here. Cows were red, isn't it? Where is the red? Let me erase it first. I don't want dots to show up there. And I'm making the cows now in the feature space. These are my cows. And let me mark horses with blue. Let's say that the horses are here. They're rather heavy, but they're not as big perhaps as cows. And so I'll mark them here. And yes, these are all illustrative. I don't think if any biologists are out here or zoologists, you may perhaps laugh at these values. I don't know how accurate these are, but we'll learn from this. So suppose this is the data. This is again your size. This axis is size, again using the white marker. This is size, and this is weight, right? Let me call it x1, x2. Right? This is it. And so your feature space is basically R2. And your target is, your categories are cow, duck, and horse. So how would you do that? The way it turns out is not that hard. It's easy to generalize. Once again, you find the center, the hilltops. And what you do is you make dotted lines. Now you have a triangle. Do you guys see the triangle here? Guys, do you guys see the triangle here?
Yes.
Yes, Asif.
Yes.
Yes.
What color is the triangle?
Green.
It's green.
So what
We're
you
awake.
do is you find the perpendicular bisector of the triangle. So the perpendicular bisector of this, they will all meet at certain point. It will be, I don't know, sort of here. I don't know. I'll just cheat. I don't know how accurate it will be. Roughly speaking like that. I'm pretty sure I didn't get it at 90 degrees here, but close enough. Here, I certainly didn't get it at 90 degrees. So I didn't place it at exactly the right place. Maybe it should have been somewhere here. Sorry. And maybe better like this. This to me perhaps looks a bit more active. May not be. Okay, but you all know that in a triangle, if you do the perpendicular bisectors, they will all meet at a point. In fact, it will be true for any polygon, right? So here we have. And so what you do is it divides the space into three regions. The region, this region, let us give this region to the cow, This, I mean, sorry, not cow. This region belongs to the ducks. This region, which I will call like this, let it belong to the horse. And this region of the feature space belongs to the cow. So if I get any data instance, let us get an arbitrary data instance, and let's pick another color for that. Suppose I take this. If I get this point here, what would you call this point? Is this a cow or a duck or a horse? Okay. Is this point a cow, duck, or a horse where I've marked it? Oh. Why is it? Why is it? Because it belongs to
It's a cow.
the cow. Yes, it belongs to the feature space we have marked as a cow. Likewise, the point here would be a horse, and a point on this side would be in the lower left-hand side would be a duck. And on the upper side, upper left-hand side would be a horse. Right? So what you do is you partition the feature space into the classes. Let me write it down. A classifier, this is an interesting observation. A classifier geometrically partitions the feature space into disjoint regions with one region belonging to one of the classes. Are we together? Now, the number of partitions will be equal to what?
Number of classes.
The number of your classes. At least, it could be more. But at least in this particular algorithm, it would be the same as the number of classes. So, guys, did we understand the linear discriminant analysis? Is it simple, guys? Huh? Let us recapitulate all the ideas. Huh? We are saying that suppose we are dealing with cows and ducks, and suppose the underlying assumption is that they form clusters, bell hill shaped clusters, then all we need to do is find the hilltops and connect them and find the perpendicular bisector. That could be a good decision boundary. The underlying assumptions is that both the bell hills look more or less identical, but they are placed at different places in the feature space. Right? That's our decision boundary. And decision boundary, the word is very evocative because it says it helps you decide whether something is a cow or a duck. That's why the word decision boundary, or in the case of three classes, whether something is a cow, duck, or a horse. And so the decision boundary is that line, which is the sum putting together the three perpendicular bisectors. Okay? So that's that. This is it. Now there is one a more complication. There is something called quadratic discriminant analysis. QDA I will just mention briefly because today is the first day. Later on, we'll talk about it more perhaps. In QDA, the only thing that you relax is that the variance of cow is not equal to the variance of duck. In other words, the bell hills don't look alike. Bell hills do not look alike. In that case, what happens is, I won't go into the theory, but much of it remains the same, except that when you have the cows, let's say the cows, the ducks and the cows, let's bring back our cows quickly, and I'll just be brief about it. For reasons that are slightly mathematical, what happens is that your decision boundary becomes sort of quadratic, I believe, in this particular case. Let us just make it like this. Huh? Do you notice that this is curved? Actually, I usually use now, I apologize. I usually use green for this. I wish there was a way to substitute the color or me not making a mistake. So this, again, the same thing. This is for your future nodes. Decision boundary is a quadratic curve or surface. When we do the lab, this will all become very real. But do you see the bend? It's not a straight line anymore. Are we together, guys? So this is the distinction between linear discriminant analysis and quadratic discriminant analysis, right? So you have encountered one form of classifier. Now I'm going to stop here today, guys, because we have learned new concepts and it will take you some time to absorb this concept. I would recommend that you read chapter 4 and only read the discriminant analysis section. Right? Don't read the logistic regression. You're welcome to read it, but it might be a bit hard. Go read the discriminant analysis sections and see now if it makes sense or if it is easy to understand in view of the discussions we had today. So now I'll stop. I'd like to give the last 20 minutes to question and answer. The one algorithm we didn't cover is the one that I thought I would start out with, but we'll do it next time because it needs a whole session of its own. It is called logistic regression. And we'll keep a whole session dedicated to that. And that would be next time. Any questions, guys? No questions. Is it clear to you guys? Is all of this becoming clear? Is it simple to understand?
Yes, sir. Asif, sir, I have a question.
Mm-hmm.
So when I read the book, I think I understood, but if you could please explain one more time, that might help.
The discriminant analysis from the
No, not the theory part, sir, like the wording, why it is called linear discriminant analysis, sir.
Oh, it's very simple. Because the decision boundary, look at the shape of the decision boundary. When you assume that the two hills look alike, the decision boundary happens to be a straight line or a hyperplane, plane, hyperplane. These are linear equations. These are linear surfaces, smooth surfaces, isn't it? Linear surfaces.
And discriminant is for the different classes, right?
Yeah, discriminant just comes from the word, it discriminates between a cow and a duck, between the classes. So discriminant is almost synonymous with classifier, isn't it? It's an old term for classification, discrimination. Remember, this was done in the 1920s, 1926, I believe, when Fisher did this original work. So the terminology from those years have stuck around.
Thank you.
Now, one strength of this discriminant analysis, whether linear or quadratic, is it is easy to generalize to many classes. You know, we went from cows, duck, and horses, 3 classes. We could go from cows, duck, horses, and I don't know, giraffes. Right? It could be easy to do that, and so forth. Right? You can add as many classes as you wish, and the discriminant analysis approach still works. As you will see, not all algorithms have the benefit of that. There are quite a few classifiers that can only distinguish between 2. Categories can have only 2. Right? For example, is it a cow or not? Is it a cow or a duck? That's all. You can't add horse to the mix easily. You can do it, but it's a sort of a different thing you have to add on top of it. So what are the assumptions of discriminant analysis? Assumption is each of the class instances are clustered around a different center in the feature space. That's important. Yeah? That may not be true, as you will see next time. But for it to work, for this algorithm to work, that must be true. The clusters are approximately Bell Hills. Is wrong. Bell Hills. Oh, sorry. What just happened? It behaved strangely. Okay. Their Bell Hills, or more formally, have a normal or Gaussian distribution. A third is only for linear. The hills look alike. If the hills don't look alike, then you use quadratic discriminant analysis. So please read it in your book. I'll send out these notes. And if you guys don't have a question, I will stop the recording. Was that clear, guys? I want to know, are these ideas clear? Did you get the concept of a classifier?
I think so.
Yes.
Good.
Yes.
Yes.
So I'm stopping the recording. Remember, guys, if you get stuck, I'm available anytime. Reach me out in Slack. And in the evening times, any evening, I'll be able to come and help you. Right? Also, there are TAs who can help you. But one thing that you must do is actually do the labs in the notes. Follow those examples and repeat it. At this moment, you guys have a lot of catch up to do. As of this moment, we are on chapter 4, which means the first 3 chapters of the book are done, which means 100 pages of the book are done. We are now marching on to chapter 4. Review the discriminant analysis section of chapter 4. And at the same time, as you do the labs, refer to those reference books.